So then, hey everybody, good morning, good afternoon, or good evening, depending on the time zone. This is Daniel, and this is the Zero Knowledge Learning Group meetup series, practically that we do with Linux Foundation Decentralized Trust. The topic is for today, I would say advanced Noir programming. It's a little bit tricky. It's not going to be really advanced. We just go one step further that we where we stopped last time practically. So it's not going to be advanced, but it's going to be like more advanced than we covered last time. And this is a learning group again, practically with Linux Foundation Decentralized Trust. We do zero knowledge and SNARK application development practically. So as usual, let me start with the logistics. Again, so this is the ZK Learning Group. Practically, it's one meetup each month. Usually, it's the third Saturday throughout this year from 6 o'clock in the afternoon, Central European time. That's like, I guess, 9 o'clock Pacific. I don't know. It's like 1 o'clock New York time or something. The idea is the following. It's 1 hour each month. Practically, it's a little bit like content driven by me. So we just keep the timing fixed for 1 hour, which is practically a presentation and then some demonstration code from my side. And then sometimes we have a time for short discussion or questions and answers, but sometimes we do not really have this time. But basically, the idea is that we got a Discord channel. I will just show it in a second. And then if you have any questions that I cannot answer really in this 1 hour, then just feel free to join the Discord channel from Linux Foundation Decentralized Trust. Go to the ZK Learning Group and then just feel free to add your questions in the chat practically. We're going to cover different topics from zero knowledge proof. Well, actually, I'm not a mathematician. I covered some of the mathematical concepts as well, but I just summarized the topic mostly from a programmer and an application developer perspective, again with some theory. So the coordination, again, it's on Discord channel. So if you just Google Linux Foundation Decentralized Trust Discord channel, you're gonna find it, and you're gonna find an invitation. So that's practically the Linux Foundation Decentralized Trust Discord channel. And then if you join, again, you can just Google Linux Foundation Decentralized Trust Discord channel, and you got an invitation link. And then if you join, we are somewhere under communities. And the last chapter of the community is the Zero Knowledge Learning Group. I will post practically every material, every recording, every PowerPoint that I cover here. And again, if we do not have the time for answering questions, then just feel free to have the question here in the chat, and then I will answer as far as I can and as fast as I can practically. Okay, so that's like the major focus, or that's like the major communication channel for coordination. And we use, of course, meetup.com. So if you're familiar with Linux Foundation Decentralized meetup.com, then you're gonna find this meetup series practically everywhere. As far as I know, it's shared with 136 countries. So practically, whenever you find Linux Foundation Decentralized Trust meetup, then you will find this online, even as it is practically fully online. So it's not related to any location. And we are having one repository as well. It's under Linux Foundation Decentralized Trust Labs. Labs are practically small projects from Linux Foundation. And while this is not really a project, but something similar, but anyway, if you just come to GitHub, and you're gonna find Linux Foundation Decentralized Trust Labs, And under Decentralized Trust Labs, you will find ZK Learning Group. So ZK Learning Group is practically like the GitHub repository for all of the material that we cover here. It has like one page with all the recordings, all the slides, and all the meetups, and you're gonna find like all the code examples as well. So it was like Circum, you find the Circum examples here. We're gonna cover now Noir, so you will find all the Noir examples here. And then later on, we're just gonna focus on application development. So practically, you will find all the application development examples, code examples here as well. But again, it's just, probably the most important is this, cover page, which contains all the slideshows, all the recordings, all the meetups, all the links and literatures throughout this practically course. So that's coordination. And again, so we just try to have one meetup in each month until the end of the years. And then there's gonna be like, there are already some small programming challenges as well. They are still not very popular, but if you're keen to solve these puzzles or these like homeworks, then there might be some Linux Foundation Decentralized Trust merge at the end of the year. So that's logistics. And then from the content perspective, we started in February with some introduction theory. Then we covered polynomial commitments, interactive oracle proofs. In May, we focused on programming in Circum. In June, we continued with programming in Circum. In July, we started with Noir, with the basics. We just continue with programming in Noir with like few more advanced things. And in September, we just gonna switch to applications. So how we build up zero-knowledge applications or SNARK applications. So in the meantime, recording just stopped. Not quite sure if it's good, but let me just continue nevertheless.
It's okay, Daniel, you can continue. It's okay. Just a bot recording, yeah.
Yeah. It's just too much here, I guess.
Yeah, but we're live. It's okay.
Okay. So anyway, in September, I'm just planning one change. We start from September. We continue from September with applications. It's zero-knowledge applications. September is gonna be a little bit like special, probably. We will cover like proof of reserve and proof of solvency algorithms instead of off-chain transactions, and it's gonna be like a special dedicated topic probably. And we cover off-chain transaction, yes, probably in October. So it's gonna be like a little bit change, but anyway, we might as well, forget off-chain transactions and then do something which is like zero-knowledge machine learning as application or something similar. But anyway, the idea is that from September, we just cover different zero-knowledge applications, probably till the end of the year. And it's subject to change. It's based on community discussion as well. So basically, it was like one wish that in September we should cover if it's possible, like proof of solvency and proof of reserves algorithms. So we just changed a little bit like the content. So if you just have any wishes, in terms of zero-knowledge programming, just feel free to drop it into the Discord channel, and we might as well have that special content as well till the end of the year. So that's generally the logistics for zero-knowledge learning group. And I'm just continue with the agenda for today, which is like more advanced Noir programming. I wouldn't say it's gonna be advanced because we're just gonna cover practically the basics. We just continue with the basics. As usual, I have one slide on ZK SNARK, then on Aztec and Noir. Then we just take a look on Noir examples, data, control structures, extensions, and libraries. We just cover how Noir can be used in application development, and some challenges, of course, still at the end, and some links, resources, and literatures And if we have time, then we can have like, questions and answers at the end. So that's the plan for today. So let me just start. And as usual, let me just start with the summary of ZK SNARK, which is, I mean, it might be boring, but I mean, if you participated in all of the previous, I mean, meetups, I mean, this slide might be boring actually. I might as well skip for the next presentation, but I mean, it's such a complex and sometimes non-intuitive field that it's just, I find it's a good idea to have this one slide on generally zero knowledge SNARK summary at the beginning. So let me just have the usual slide. If we speak of like ZK SNARK or SNARK, usually, or zero knowledge generally, usually we think of a model where we have like two roles. We get one prover and we get one verifier. And then usually we have something which is like a domain problem. It's like Alibaba Cave might be a domain problem, or like proving that I know pre-image of a hash function might be a domain problem. But nevertheless, this domain problem might vary. And to express this domain problem, we have something which is a computation. So computation is a little bit tricky in this zero knowledge field because it's not necessarily expressed by a classical computational, I mean, with a programming language, a classical like object-oriented programming language, but usually it is expressed with a mathematics thing, which is like an arithmetic circuit. So we can have like computation, which is like C, which has two inputs, like it has X public input, it has one W, which is a private input. We can call it a witness as well, and it results a function, but we can actually formulate it in a predicate way as well. So it's basically, it's not a function, it's an element of a field, so that we can formulate it as a predicate as well. So if that's a predicate, then it results to true or false practically. These representations are equivalent. So that's somehow our domain, and then we can somehow program or specify this domain. Again, it's usually we think of arithmetic circuits if we think of this computation, but in practice we don't necessarily deal directly with arithmetic circuits. Usually we have something which is a high-level computation. It is sometimes a little bit questionable how much high level is this computation, but anyway, usually it's a little bit higher or more higher than just an arithmetic circuits. Then we can comply from this high level computation or expression to an arithmetic circuit representation. From an arithmetic circuit representation, we can somehow compile to practically discrete polynomials. And these mathematical polynomials gonna express for ourselves the zero knowledge and SNARK properties basically. So that's computation, and we get a prover and we get a verifier. And what a prover does, the prover tries to prove practically a statement, which is a computation here, that this statement is true. And again, this statement might have public input and private inputs as well. And the verifier gonna accept or reject this proof. And what's important is that the verifier can accept or reject this proof without seeing basically the private input of this proof, of this computation, of this expression, for instance. So again, from a mathematical point of view, it's like, I mean, we don't speak of like roles, we speak of like algorithms. So we get like two algorithms, we get a prover, and we get a verifier algorithm, and the prover algorithm is just gonna take the public input, the private input, and practically generates a proof. There's like a special preprocessing argument here as well, which is not so important from a global point of view. And we have a verifier algorithms as well, and the verifier algorithms takes like the public input and the proof itself, and it either accepts or rejects this proof. The verifier algorithm has like a preprocessing argument as well, which is again not so important at this moment. So the point is, one important thing is that basically the verifier does not see the private input. So basically, that's what gives us for something which we think of like zero knowledge properties. So I mean, if you think of that, you want to give a proof that you know basically a preimage of a hash function without revealing the preimage of that hash function, then usually the preimage is the private input, and then basically you just generate the proof, and the verifier gonna accept or reject that proof without basically knowing the preimage of the hash function. So that's what the zero knowledge. But basically, if we think of like SNARK and not just zero knowledge, SNARK has several properties which are important. First, it's succinct. Succinct means that the proof is small. Proof is small in the sense of size and in the sense of verification time as well. So basically, it gives us special application areas where we practically create a proof of a pretty complex computation, and this proof gonna be short and fast to verify. And then in this sense, we can just prove that we just executed a complex calculation, and we can do this proof in a short size and very fast verifiable way practically, which is of course pretty practical for blockchains. It's non-interactive, so basically you can think of interactive proofs that there are several iterations between prover and verifier. But basically we don't like it in blockchains, so basically it's best if we have just one proof, and then just based on the proof without any further iterations, the verifier accepts or rejects. It's an argument of knowledge. Argument of knowledge means that basically the prover knows something, the prover knows this private input practically. That's the argument of knowledge. And it has several further properties. It's complete, so basically if there's a proof, then the verifier gonna accept. It's knowledge sound. It means that if the verifier accepts a proof, then the prover really knows, like a public X and the W input, private input witness. From that, this proof can be generated. That's like solid knowledge soundness. And we get the zero knowledge property, which is not necessarily required. But the zero knowledge just means that this W private input is not known by the verifier. So that's SNARK. And then we covered last time the basics of Noir and Aztec. Noir is more important because, I mean, Aztec is a very interesting framework, but actually it's not so much our focus. What we cover in this Zeek learning group, we just take a look of examples of zero knowledge programming languages, and Noir is a very good example. And you can use it with or without Aztec as well. And Aztec is a very interesting framework, but it's more Ethereum oriented, so might not be so much focus in Linux Foundation. But again, it's very, very interesting nevertheless. So the point is from Noir, it has like, again, so Noir is basically, if you think of, we got like this high level computation language. So we want to have like a way to express our domain knowledge, our domain problem in a way. Like that's gonna be like the case of Alibaba or the parameters of hash function, and we don't want to do it with polynomials. We don't want to directly program arithmetic circuits either. So what we need is like a high-level computation language, kind of as high as possible. And Noir is targets actually. The idea of Noir is to have like a high-level programming language for expressing like domain problems for zero knowledge. It's a Rust-like syntax. Theoretically, you need limited cryptographic experience, so you don't need to be a cryptographer to like implement zero knowledge related algorithms or problems. One more innovation, or one important innovation, it does not directly complies to one specific prover backend or prover, but instead it has a way to compile to an intermediate representation. And this intermediate representation can be actually used by several different prover systems. So that's like one big innovation, for instance. So this is a classical flow. You get a Noir code, there's a compiler, it compiles to this arithmetic intermediate representation. That's ACR language, and then this can be like optimized or compiled further to like a specific prover backend. This is like Battenberg, if I'm not mistaken, but you can use like a simple gross 16 kind of prover as well. And based on this backend prover, you can create a proof and you can verify and stuff like that. So that's one innovation. You can use different backends basically. It's one big advantage of Noir. It's more like platform agnostic. So in this sense, this A series pretty much, it can compile to different prover backends. And there's even a list of like which backends are supported at the moment and which not. So this is the language itself and the concept. And of course, you can use everything with Aztec. It's pretty much driven directly by Aztec. But it's like a more general or a more complex system. It's actually a layer 2 rollup system on Ethereum. It has private function possibility. It has practically a two-part layer 2 rollup system. So it's usually, we say it's like a privacy preserving layer 2 rollup system because it has like two parts. One is a public layer 2 and the other one is a private layer 2 rollup system, and everything is programmed by Noir, of course. So practically there's like public and private state. There's like an account balance space ledger, which is public state, and it has like a public Noir kind of Ethereum virtual machine as well, and it has like a UTXO ledger as well, which is like private basically. So in this sense, you can create like privacy preserving layer 2 applications on the Ethereum, and of course the main programming language is Noir, of course. So let me just continue with Noir with some examples. And I'm just gonna actually demonstrate the basic programming possibilities with Noir. So what I'm gonna do first, I'm just taking. So we're just gonna cover code samples practically from here. Anyway, you find everything in the GitHub repo. So if we just go to the GitHub repo and you just switch to Noir, there should be like Noir samples, and you're gonna find all the samples here. So these are the samples that I'm demonstrating. Actually, these are like core language elements from Noir. And what I'm using is that we got something which is a Noir playground. So practically you can install everything locally. It's possible. It's just for a simple demonstration purposes, or if you just want to play with the environment, it's just easier to use this Noir playground. Anyway, you find a link for this Noir playground. That's the online playground here. So basically, it's actually on the slides. Okay. So let me start with some coding then, and let me have like a hello world Noir. So practically, what we're gonna have here, it looks that way. That we got, it's pretty much a Rust style. So we got more or less the Rust syntax. We get something which is field. These are like that's the basic data type of Noir. These are like fields like 256-bit prime fields. And then we get some simple types as well, like integers, booleans, even strings, but actually they are derived from this fields type. So basically fields is the basic. Sometimes it's just easier to use like, integers, booleans, strings and stuff like that. But anyway, I'm using this hello world for the first one, and it looks that way. It's a Rust style syntax. We got like two inputs. One input is public, that's like the public input, and we get like one private input as well, that's X practically. And it's a function, so basically it resides one element, which is a field as well. And what's important here, that's basically the constraint. That's what we call it's a constraint. It is compiled to an arithmetic constraint. For the first one in intermediate representation, it just says that X should not be equal to epsilon. So basically, that's all. That's our constraint, and it resides actually X. It's not so important, but basically, we might as well want to use somewhere. So if we have that code, we just say run. Supposing that this environment is working, it's just sometimes a little bit tricky if I zoom. So let me just take a look. I guess it's with the screen sharing, it doesn't really. So let me just give a shot and then just opening Chrome. So just give me 1 second. That's the usual demonstration effect. It's like the disadvantage of live coding always. So that's our environment, and let me just copy paste the code from here again. And then let me just set it. And let me just run it. So it's working. So it looks like there's like this console. So basically, if it looks great, so at the moment we get the code on the left side, we get the two inputs on the right side. It's like X and Y. So basically, Y is the public field, and X is the private field. And if everything goes well, then basically we get here basically everything: the public inputs, the witness, and the proof as well. So basically, that's all. And then so we can just copy paste the proof as well and take a look if you want, but it's like the cryptographic magic basically. And if you just change to like 1010 and we say run, then basically it says the circuit execution failed. Let me just take a look if I can zoom in more. Cannot satisfy constraint. Okay, so this is like hello world with Noir. So let me just continue. And let me just have the next one, which is like some simple types. So it's gonna simple types Noir. What I'm doing basically, I'm just copy pasting some simple types. And then basically, so the code, so it's a little bit tricky because I don't see the syntax highlight unless I change to, the file extension is an R for Noir, but I just don't see the syntax highlight unless I change it to RS, Rust. So basically, I just change it basically, that it looks that way. So what we can have like, of course, inputs. We can have different integers. We can have signed and unsigned integers. So basically, I have just here one unsigned integer, I have one integer which is like -1, so it's a signed integer. Of course, the key logic is having these asserts, so I just say that like input should be equal to x plus x. I can have some boolean as well, which is like false, and I can even use like strings, which is like hello world at the moment, and I can even use some string operation as well. So at the moment, message should be hello world. So that's my code basically. And if I just run it, basically I said that it's not satisfied the constraint. It's because x equal 2 and input should be like 2, so that should be like 4. And if that's 4, then I should have like a successful verification. So I get the proof and I get the witness here as well. So these are like simple types basically. Then what I can have here, I can have like complex types. And again, so this might be like, not very much fancy, comparing with like a, I mean, a classical programming language. But if you think of like Circum, in Circum, you just use like, almost directly arithmetic circuits. So I mean, in comparing with like programming directly arithmetic circuits, I would say it's something which is, yeah, pretty cool. So we can have like arrays. And again, what I'm just doing here, I'm just retyping to NS, so I got this syntax highlight. So basically, I have like different arrays. As usual in Rust, I can have like a non-mutable array. This one is my non-mutable array. It's basically a fixed size, so it's pretty important. And all arrays in Rust are fixed size. I can just refer to the elements of basically of my array that way, first and second. I can of course create a mutable array as well. So again, that's basically there's this crazy Rust logic behind. If that's like a mutable array, then I can basically like at the moment I just create an asset which is like compiled to an arithmetic circuit that my 0 or first element should be equal to 1, and I just, as basically this is a mutable array, then I just reset this first element to 42, and then basically I just make sure that this element should be 42 with like an arithmetic constraints. And then basically I can have this, I mean, I guess this is like a classical Rust syntax as well. Like I can initializing these elements with like repeating. So if I just define my array that way, then basically it's gonna be an unsigned 8-bit integer, and I will have like a 32 length array, which is initialized in a way that each element is initialized to 1. So I can just pick like one item, it's like the 12th item, and then I can make sure that that's 1. So these are the arrays. So if I just put to the online playground, then basically I can take a look if that works. And I'm not quite sure which are the assets I have, but basically I'm gonna have one asset which says its first item is 1, and then that's 42, and then its worth should be 1, so basically that should be run without problem, and it looks great. So basically the constraints are satisfied. It's, I guess I don't even use this input, so basically I can write here anything that's gonna be this, the generated constraint is gonna be satisfied, and I will get the proof basically. Okay, so that was simple, that was array. And the next one is slice. It looks that way, that the arrays are statics in slice. So basically, if you initialize an array with like, I don't know, size of the 10, then you cannot add like further elements to that slide, to that array. So basically, if you want to use like a dynamic array, then basically you should use slice. And this is like a slice. So basically, this is like a mutable slice. And then you can just push. I mean, you have like several how can I say, these are like atomic operators on your slice. So you can like push a new item to the end of the array. You have like other operators as well. So you can like push at the beginning of your array. You can actually insert in the middle of the array. Again, I mean, this is not actually array. This is like a dynamic array, which is a slice. So you have like a list of atomic operators that you can use. So here what I'm having, I'm just having like, I think that's like a 2 lengths, and then basically I will just push in a stack way one item to the top of the, or to the end of the of my array, which is 6. So basically the new length of my dynamic array gonna be 3, and basically the third element, actually I just write 2 because we start with 0, so there's a third element gonna be 6, which is like, you know, I mean, this push operator, and I just return 4 with the length of my slice. I'm not quite sure why, but nevertheless, that's like the idea for a dynamic array. So let me just take a look if that works. And yeah, I don't even have like input, so basically these are just, I don't know why are these here. It's just probably the online playground. I could have like one input here, but I don't really use inputs at the moment, so basically everything looks good. Yep. Okay. So that was, I mean, not all, but basically I have like 2 more things which are, you know, pretty much common in programming languages, but you know, it's just not necessary, so trivial in zero-knowledge programming. I have like tuples. My tuples. So these are my tuples. I just rename it to Rust, and I get the highlight. So basically, this is a 1, 2, 3, 4, 5 tuple, which I define here. I just initialize as well. It's just practically 5 numbers, and then basically I can refer elements to the tuple as, you know, as usual. It's like 0, 3, 1, 2, 3, 4, 5, and then I can write practically constraints with it, with this assert statement in a way that, you know, I mean, 0 should be fine, 3 should be 8, and then input should be 25 at the moment. So it's nothing surprising. It's an immutable at the moment, but you can do it in a mutable way as well. So let me just take a look if that works. And basically, if I just run it, it's successful, but basically we can check that I'm not cheating because we get one input basically, and the input is like the last element for the tuple that I initialize with. So if I just write here like 10, then actually the constraint should not be satisfied. So practically that's it. So these are basically the complex. Oh, sorry, I got one more complex type, and that's basically the struct. So as usual, I get a struct as well. It's again pretty normal in any kind of programming language, but basically comparing with like Circum, it's pretty cool. So I get a struct, which is an animal. It has like, as usual, 4, you know, I mean, fields. I mean, animal can have hands, legs, and eyes. I'm not quite sure if that's true for all animals, but anyway, it doesn't matter. So it has like hands, which is a field, legs, which is a field, and eyes, which is a field. I got one main function. Practically, I just create a dog based on my animal with eyes 2, with hands 0, and with legs, which is like 4 at the moment. And I just write a few asserts. Basically, I just create practically constraints which gonna be compiled directly to arithmetic circuits, that the dog.ice equals 2, the dog hands equals 0, and the dog legs equals 4. So if I just compile it again, that should basically work. Okay. So if I just run it, it's successful. I mean, I did not even have like input. I could have like some public-private input here as well. So these are the data types, and I got control structures as well. Again, so these are nothing special basically, but if you just compare with like Circum, it's pretty cool. So as any kind of programming language, I got like if, then, and for loops. These work pretty much the same way as in any kind of programming language. So I got one if then, basically, I just changed to Rust. And then basically it looks that way. I got like, if, that's like an embedded if, that's like an else, and that's like the outer if, and then basically overall I have like different variables which are initialized. I just check basically if that variable is equals to something or doesn't equal to something. I just reset value, and basically at the end I just have like asserts as well, and I got my second assert basically somewhere here. So again, it's nothing special. It's like a classical if then. Again, you might be wondering why it is so important. So if you think of like Circum, doing the same thing is pretty crazy, because instead of if then in Circum you should use something which is like a special circuit that mimics somehow basically this if then, which is pretty crazy. So I did not succeed to compile because probably I should have like something which is, I don't know, 5, or x should be 5, or sorry, input, if input equals 0, let me just try with 0. Yeah, it works with 0, but anyway, it doesn't matter. It's just demonstrated the if then, which is pretty simple as in any kind of programming language. And we got something which is a loop, which is a for loop. A for loop works in a pretty same way as in any kind of programming language as well. So basically, I get just for I in the range of 1 to 10, and basically I just have one input or one variable which is x. It is initialized to 0. I just add it with some input, and basically I just increase it basically, and at the end I have something which is like, that's like an asset, which is a constraint which compiles to arithmetic circuit, and it makes sure that basically this one is like input plus 10. So basically that should work actually for any number. So that's like a classical for loop. And again, it works. So actually it works for any number, because as I remember, I wrote the constraints that way. So that's cool. We got like 2 more loops as well, which are general loops and like while loops. And it's gonna be like more tricky. It's because the problem is that Noir cannot really deal with loops which might be unlimited. So for loop is always limited to a certain number of iterations. But as soon as we have like while loops, or basically the general loop is like repeat loop, it might not be it might not end at all. So basically Noir cannot really have this functionality. So we got one special thing, which is the so-called unconstrained logic. And it looks that way, that if we can use unconstrained logic as well. If we use unconstrained logic, then basically there's not going to be any circuit generated based on our code, which might be surprising why we use it. But basically, there might be like computation which are complex in a way. that we don't want directly that our code generates like constraints, arithmetic circuits, but we want to have the computation, and after the computation, we just want to make sure with like additional logic, additional constraints that our computation was correct. So that's the possibility with unconstrained logics. And of course, I mean, as a developer, you should pay extra attention that in your unconstrained logic, you just cannot. I mean, you just make sure that basically the constraints after your unconstrained logic are valid and cannot be hacked, because otherwise you have a problem. So basically, you can use while loops and general loops as well, but only in an unconstrained way. Okay. I mean, I think I have a few examples as well, but basically, you can take a look on yourself. And then we get, of course, logical operation. It's like bitwise logical comparison. So I just show it basically. We have somewhere logical. These are like logical operations. So basically it looks that way. It's just, you know, it's just an OR, nothing spawn. So we get an if, and basically we use an OR basically as usual. And we get a lot of like different logical operators as well. We get functions, so we can use functions. There's always like a main function. The main function is always like the initial starting point of our domain calculation, but we can have sub functions as well. And again, we can have something which is unconstrained function. Unconstrained function means that basically there's not gonna be constraint generated, and then you cannot even use directly constraint in your unconstrained function. But of course, after your unconstrained calculation, you just make sure that it's correct somehow. So basically, it can be basically tricky. And then we can have methods as well. So basically, I mean, if you're familiar a little bit with Rust, there's not like classical object orientation, but basically you can have like structs and you can write methods to structs. So basically, let me just have like one example with a method. This is like a method. Basically, it's pretty much very simple. We got like an apple, which has one property, which is size. So that's like our apple struct. We can have an implementation for our apple struct, which is like, it has like two parameters, two methods. One is a constructor. Basically, we just create a new apple with a size 2. And we have one more, which is like querying basically the size of the apple plus 1. So nothing special. And basically in our input, we can just initiate one new apple struct, and we can use this apple struct. We can use the method of our struct, like get size in our logic in a way that basically we use it with asserts. So basically there's gonna be directly constraint generated based on that. Let me just take a look if that works. It just takes like 30 seconds probably. Yeah, it works, so nothing special. Okay, perhaps I'm having one unconstrained. I have one function here, but it's just pretty simple. I don't have unconstrained example at the moment. Okay, so these are basically the basic elements from Noir, and then the point is that you got like a repository, which is this awesome Noir repository. So if you want to develop something which is like more complex, then the idea is not to develop it from scratch, but take a look on this repository, because you find a lot of different things. You find like additional data type implementations, like big numbers, floating points, complex number, fixed points, date and time. You find different like data type manipulation. I mean, these are not even data type manipulation, but like extra things like matrices, statistics, text. You can find a lot of cryptography primitives. I mean, implemented with implementation. It's like elliptic curve cryptography, hashes, encryption, signatures, and so on and so forth. So basically, just take a look on this repository. You will find all the like extra types. So these are like big data types, additional data types. These are like, matrix operations. This is like text, string utils. This is like cryptographic. So you can use like, you have the different hash implementations like Ketchup, Poseidon, SHE, 256, and so on and so forth. You find like encryption, you find signature implementations, Merkle trees, message authentication code, is in pseudo random number generation, and so on and so forth. So it's like a pretty cool like library. And well, the last question is, how do you build application based on Noir? And basically it looks that way, that you have like two options. The one option is like you use Noir with some custom application. So basically you can have a custom backend prover, or you can have your own backend prover, or you can just pick any kind of backend prover. You have the Noir JavaScript. You can even have like a Solidity prover, generated Solidity prover, and then use everything in your own application basically, and you integrate everything as you want. That's like a custom application. And then of course, if you program Aztec, then you can program your Aztec smart contracts in Noir as well. So here you have like utils for Noir, storage contracts, public, private, internal functions, public and private state management, and a lot of things. I think I have like one example here, which is like, again, it's not an application, but it's just kind of very simple Fibonacci series. If I'm not mistaken, it has like one public input and one private input and the public output, and then basically it just iterates to 3, and then it just calculates the Fibonacci series in a way that the first item of the Fibonacci series is like kind of an input, which is not necessarily 1, and then basically it just makes sure that the result is output. So basically it's just like kind of a proof that a private input, and the private input is like the initial starting point of a Fibonacci series, which is after 3 steps has this output basically. So it's kind of something similar. Just take a look if that works. So basically it looks that way. This is my Fibonacci, and then basically I get just one input, and the output should be, I think it should be like 3, and we get it successful, but like if you have like 2, it's unsuccessful. So basically if you just start the Fibonacci with 1 as it is, then after 3 rounds that should be the output 1, but this input is basically private, so basically that's like a proof that a private input of a Fibonacci series that after 3 rounds results in 3. So it's something similar. Okay, this was just a very simple application. So basically we slowly reach the end. I don't have like full application example, but if you just take a look like in Aztec protocol, Aztec starter, you have like full implementation for like blind voting in Aztec. So you can take a look, and then you can start develop for Aztec. Even with like Noir, you have like starting point for custom application development as well, if you need like full applications. So basically that was the content for today, and then we have like developer challenge for today as well. So the idea for a developer challenge for today is that develop a Sudoku puzzle with the help of Noir. You can just run everything in this Noir playground. I mean, it's a little bit tricky. I'm not quite sure. So it's after a certain point, it's just not easy to scroll. but perhaps it's just because of zooming. So perhaps if you don't use Zoom, it's easier. I'm not quite sure how big code you can here compile or run, but anyway, I leave it open how big Sudoku you want to use. So it might be like 3 times 3 or 9 times 9 as usual. But again, you can have just a very simple Sudoku as well. It's like 3 times 3 or something. And we have some links, resources, and literatures as well. Basically, I'm gonna share everything you can find everything in the GitHub repo as well. So that was for today. And then actually we have like 2 more minutes. So yeah, I'm pretty much tough, yeah, pretty much in time. So I would say we can have like 2 very fast questions, and otherwise I would just suggest that you use basically the Discord channel, and then we just go like, I mean, I'm just gonna try to answer everything in an asynchron way, basically in the chat. So let me just read the chat if there's like any question. So basically the webinar is streaming. There's gonna be a recording as well. You can find the recording in the YouTube channel. I'm gonna share the recording in the Discord channel as well. I'm gonna share the slides as well in the Discord channel. So basically you will find all the information. Anyway, you will find the links basically in GitHub, in the Linux Foundation Decentralized Trust ZK Learning Group. So you will find basically everything. Yeah, actually, yeah. So Noir is not it's. I'm just reading the question. It's just Noir is not a absolutely general purpose language. It's based on Rust, but it's more like a domain specific language for developing like zero knowledge applications, possibly with the knowledge of having like I mean with the need of having like deep cryptographic knowledge. So that's basically the idea. Yeah. So it's there's one question how mature Noir is actually, and it's pretty hard to say. It's I think it's like in a few things are still in like null points, as you see, like Barettenberg. Actually, this is Barettenberg. There was one question, so if I just misspelled it, that's Barettenberg is the correct way of spelling. So Noir is in 1.0.0, but Barettenberg is still in version which is like less than 1.0. So it's a good question. So I would say generally, I mean, the whole zero knowledge stack is pretty new. If you're looking for like frameworks that are already like 3-4 years in the market, that's like Circle probably, which is production ready. Noir is new, but it's developing pretty fast. So I don't know. It's up to you. Up to your risk appetite if you want to use it in a real project or not. So I would say we just reached our time. So I would like to thank you very much for your attention. If there's any question left, then just feel free to use basically the Discord chat, and I will try to answer everything as fast as I can. Otherwise, I would like to thank you very much for your attention. And then, well, as I mentioned, next month, we're just gonna cover proof of solvency, proof of reserves algorithms. It's gonna be probably not Thursday, but something which is the 16th of September, if I'm not mistaken. So thank you very much for today, and then see you next time.